Okay, welcome back to Satellite Communications and Navigation Systems. This is lecture number, I think it's 18. Nope. And this is the week that you are watching videos on detection theory, and forward error correction coding. We talked some about detection theory and work to digital modulation problem as an example that uses some of those ideas. And today, what I'll do is give a very brief overview of forward error correction coding, explain what are the high points from the video that I want you to take away. And then I have a little supplemental lecture on how one of the most common video transmission formats, DVBS2, works. And you'll see that the last, 10 lectures that we've done on the topic, we can now kind of put all the pieces together and explain, you'll see elements of all those previous lectures being described in the DVBS2 standard. You've got a project due for the distance learning students. If you haven't done so already, let me know what project that you've selected. I've not assigned the third homework yet, but I'll do that by next week for sure, because it's a radio location based homework involving GPS. All of next week is pretty much our GPS lectures, how GPS works. And then after that, that's it. The Monday after next week, you all have tests, test number 2. And then that'll open the test number 2 window period for the students on distance learning. And that's it. No more lectures. You get to just work on projects. Hopefully you'll get to relax a little, get caught up on your Atlanta video courses. And the month of April will be mostly projects for you. Homework, I will probably just let homework 3 float and be due maybe the week after all test number 2. So I won't be here to physically collect it. If you have the ability to scan it, for those of you that are here, send it. Distance learning, you have to scan it anyway. So that's not a big deal for you. I'll be back in Atlanta grading them. Okay. Any questions about course mechanics or? Okay. Well, let's talk about, I don't like to go too grossly into standards because there are actually lots of different digital communication standards. But one that you should be familiar with if you work in satellite communications is the Digital Video Broadcasting Standard. We're going to talk specifically about version 2 for satellites. I have to give some credit here too. Back in 2011, Professor Matt Valenti came down from West Virginia University, gave a fantastic lecture on this topic in my SATCOM class. It was recorded, I put it online, and of course over the years Georgia Tech has managed to pull the plug on my video server and did not migrate the videos. So maybe one day I'll dig up the video, the MP4, and reproduce it for YouTube. Or maybe I'll try to get Matt to go ahead and start his own YouTube channel. But some of the notes here I culled from his notes on that topic because it was such a good talk. So I want to give credit where credit is due. So DVB is actually a family of open standards for video broadcasting. It's maintained or published by the European Telecommunications Standards Institute but it's maintained by an industry consortium. It's an industry consortium of, I don't know, several hundred companies actually that get together and argue about what should be in the standards or not. And it's actually a family of digital video broadcasting standards that includes standards for satellites, DVBS, the first one, DVBS2, which is the most popular one nowadays, and then DVBSH. There's another set for cable. Not surprisingly, this is called DVBC, and there's a DVB-C2. You see there's kind of a similar evolution where the first 1990s standard for digital transmission got supplanted by later standards that were developed in the 2000s that kind of took advantage of the latest and greatest telecommunications ideas. And then there's another one for terrestrial broadcasting, DVB-T for terrestrial. Again, DVB-T2 and a DVB-H. And this is the one we're going to talk about today, DVBS2, since it's so popular for satellite. Its forerunner. Now, if you think about it, it makes sense that we have different standards for these different media, right? Because the satellite channel is very different from the cable TV channel, which is very different from broadcasting in the open air terrestrial ways. What are the ways that you think terrestrial, cable, and satellite differ from one another? Can anybody think of some ways that they differ from one another that would affect why you would change your standard? Start thinking like systems engineers now. Distance, that's right. Which of course translates into path loss. So we would expect the most path loss on average in our satellite links. So you'll see that the modulation is kind of tailored for that. By and large, satellite uses lower order modulation, small constellations, QPSK, ApSK, a couple higher order modes in case you do have some extra link margin. But Muliang is right, the extra distance means that by and large we're not using the higher order constellations that cable, for example, would use, or the high order modulations that cable would use. Cable and satellite do resemble one another in the sense that you usually have fairly clean, predictable channels. You don't have intermittent fading too much. Satellite, you got to worry about rain fades, so that's an issue. But cable, it's a fairly predictable channel. It doesn't vary with respect to time. There's not a lot of multipath or small scale fading. Those are all things that you have to worry about in the terrestrial wireless channel. So not surprisingly, those transmission schemes are going to reflect that. So the forerunner, DVB satellite, digital video broadcasting satellite, used QPSK, so it had one type of modulation with a raised cosine roll-off factor of 0.35. So the pulses that you transmit in the time domain look kind of like a sync function but they roll off a little faster. Roll-off factor of 0.35 means that you took a 35% increase in bandwidth in order to allow the signal to roll off faster and be truncated quicker in the time domain. So that is just a hardware limitation. And then it uses a channel code which is a block code called Reed-Solomon coding. Now, you'll recall on our lecture on forward error correction coding that we had two flavors of forward error correction coding. Now, keep in mind, forward error correction coding is different from just simple error detection codes. Like you've probably all used CRCs or parity bits, or you've seen material that you know what that is. That's basically where you put a bit or multiple bits at the end of a transmitted sequence that allows you to detect if something went wrong. And it's usually some sort of combinatorial algebraic operation on the transmitted bits to give you one or more error detection bits. The most simplest one is the parity bit check, right? You say, send a bunch of ones and zeros, and you exclusive OR them all together, right? And that basically tells you what you get is a 1 or a 0. You get a 1 if you have an odd number of ones. You get a 0 if you have an even number of ones. And so if you make one bit error in that block of data that you sent, it's very easy to detect. You look at your detected data and you do that operation. You say, wait a second, there's a mismatch. I need to throw away this data. I don't know what's bad about it, but I know that an error has occurred. And of course, the nice thing, the bad thing about a parity check is that if you make two detection errors, that could disguise itself as a proper transmission. And so there are more complicated schemes involving things like the cyclical redundancy check, where you append multiple bits at the end to detect the potential for more complex errors. But keep in mind that there's almost always, and unless you're physically retransmitting the data, there's always a way to make a set of errors, however low in probability, to mask the error detection capabilities of a code. You just hope to design a code that minimizes that probability of happening. Forward error correction is a little bit different, though, because in this instance, not only are we adding bits to detect errors, but if we add them in the right way and enough of them, then it gives us the ability to correct the error. And that's really how you make the most of what could be potentially a lossy communication system to transmit a virtually error-free signal. We never say exactly error-free because you would need infinite complexity to achieve that. But once you get down to bit error rates of 10 to the minus 7th, for example, that's considered, virtually error-free. Anyway, the Reed-Solomon flow is a block code, so that means it operates on blocks of data, taking an n number of code bits in and outputting another k code bits out, for example. K is always greater than n in that instance. And you therefore increase the amount of physical data bits or coded data bits compared to the actual data bits that you're sending, raw data bits. And so you're taking a hit on the actual transmission date because you got to basically feed these schemes at whatever rate that they're designed, these modulation schemes. And therefore you're shrinking your real data rate effectively in order to make it the data that you actually do transmit more reliable. The other type of code other than a block code is a convolutional code, which is basically a sort of free-running method of coding. It's very easy to implement in hardware. Ultimately, it has the same performance limitations that a block code has. You need more complicated convolutional coders to be able to achieve closer and closer to the Shannon channel capacity theory. But anyway, we have a whole lecture online about block codes where we discuss some Reed-Solomon codes and other things. There are whole courses you can take on that. When you get to DVBS 2, this standard was proposed in 2003 and ratified in 2005. And the goals were to improve spectral efficiency, that is the bits per hertz that you send, over the original DVB standard by 30% at least, and offer more diverse services. So for example, remember in the early 2000s, we're starting to talk about high definition TV. We'll need higher bit rate for that. So that's one thing that the standard was changed to accommodate. Backhaul operations, like video links for news feeds and things that weren't necessarily commercial grade, but you may want to take a satellite link or part of a satellite link and transmit that to video signal. Internet downlink. Could we use this physical modulation scheme, this protocol, to also transmit internet data, which means overall you have to be able to ramp up the reliability. Data is not like video where you can, data is less forgiving than video. So there had to be a way to accommodate that. And then large scale data content distribution. Sending newspapers electronically to people or something like that, where you're broadcasting data. And so the basic specs, what do we need to design or specify a modulation scheme? Well, we need to know the signal constellation. And just as was discussed at video 06, the problem is there is no one-size-fits-all modulation scheme that we've come up with that's good for any radio channel all the time, especially if the signal-to-noise ratio fluctuates. And we can get fluctuations like that in satellite TV. If we're operating up at 11 or 12 gigahertz to broadcast a satellite signal, a video signal down to Earth on the downlink, well, now we're talking about a region where, okay, there'll be some slight path loss changes as I move from maybe the latitude, the longitude of my geostationary Earth orbit satellite to, a few hundred miles to the right or to the left. That might make a dB or two difference. And that can actually change the performance of a satellite link. There'll also be weather, right? Now we're talking about high enough frequency where rain fading, even a modest rain might add 1 or 2 extra dB, which will make a difference in the satellite link. And so the signal constellation for video transmission needs to be adapted to make the most of the radio spectrum. That's different than the first DVB standard, which was simply QPSK. Let's use QPSK all the time for our transmission link and hope that's good. And if it works for the worst case scenario, it'll work for the best case scenario. Well, for DVBS 2, we actually use 4 selectable constellations. If things are bad, so I'm going to sketch the IQ diagrams here. If things are bad, we use QPSK. I'll draw out my standard pi/4 QPSK constellation. Pi/4. And of course you can transmit 2 bits per symbol. If I have a little more signal to noise ratio, I can use 8-ary PSK, 8-ary phase shift keying, which allows me to transmit 3 bits per symbol. There are 8 combinations for 3 bits. 2 to the 3 is 8. And so I put 8 symbol points in a circle such that all the points are the same distance from the origin on my I and Q diagram. We know in this class that that's actually good, right? Especially for a transmitter like a satellite that may have some nonlinearities. Why do they have nonlinearities? Well, at some point, your high-powered amplifier, you always want to operate near its nonlinear point because that makes it more energy efficient. This is the thing that draws probably the most power, the single thing that draws the most power on a real geostationary Earth orbit communication satellite, that power amplifier. So in order to make it efficient, you got to tolerate some nonlinearities. Well, using QAM is not a good method for transmitting through a nonlinear power amplifier because, as we said earlier, it distorts different parts of the QAM spectrum differently. It can clip and kind of smoosh in those corner points, and that makes it very difficult to detect, especially since you never get a QAM constellation arriving perfectly intact. It's always rotated some random number of radians in phase when it gets to your receiver, so you're not exactly sure, at least first off, where to draw your decision points. So there's a lot of benefit. QPSK, of course, has the same principal property. All of the pulse points have the same average power, or same energy. And that means that when an amplifier starts to clip, i.e. its amplitude changes, you're going to get detectable constellation. You shrink it down in size, but you don't change the decision points. This is particularly true for satellites because some of satellites, in order to accommodate high power levels, will use things like traveling wave tube amplifiers and other types of amplifiers that have extra nonlinearities compared to a standard solid state amplifier. The amplitude of the signal will actually fluctuate. It can fluctuate away for these 2 constellation signals, not going to change anything. The next, if you are really good though and have a nice clean channel, then you can use something called 16 ApSK. And ApSK is another word for, just call it amplitude and phase shift keying. This is a form of quadrature amplitude modulation, but oftentimes QAM is reserved for that nice grid-like constellation. When you say the word QAM, technically that's amplitude and phase shift keying as well, but that grid of points that we drew in previous lectures is sort of like the first thing you think of. So that kind of signal defaults to being called QAM. Here we're going to send 4 bits per symbol. And what we'll do is we'll send QPSK on an inner ring, and then I put 12 additional points equal spaced on an outer ring. So you see I now have 2 power levels. I have an inner power level and an outer power level. And then if you're really good, if you've got a nice, beautiful, clean signal with high signal to noise ratio, you can transmit QPSK on the inner circle. You can do another 12 points of phase shift keying on the outer circle. And then you can put 16 points on an even larger circle. So it helps to arrange things in circles, because this means that with some pilot symbols you can estimate how nonlinear the system is behaving and kind of adjust your decisions accordingly. So here's our inner circle. That's all one power. All these signals are all another power. And then finally, all these are a third power level. And so if there is a little bit of compression, especially for that outer level, outer level of symbols transmitted, what is that going to do? Well, it's going to squish it closer to the second ring. And if I have some pilot symbols, I can maybe transmit some first symbols on the outer ring and some symbols on the inner ring, kind of in a predetermined pattern, so that I can compare that and say, well, look, it looks like there's some nonlinearities here. Maybe I just need to redraw my decision boundary for this constellation, taking into account that I've compressed it a little. So so first I determine, just by looking at the power of the signal, which is very easy to do and to measure in hardware, you say which ring is this symbol on, and then once you've determined the ring, then you pick the phase and try to estimate the phase and figure out what the symbol is from there. But as you can see, this is 32 ApSK, because if I count and I've properly designed it, I should have 32 constellation points on my IQ diagram here, and that of course allows me to transmit a whopping 5 bits per symbol. Nope. Exercise music. Let me give you a problem to look at while the music is going. The symbol that's being transmitted here has a roll-off factor of 0.2. So see if you can estimate, if I use DVBS, the original standard, with its roll-off factor of 0.35, how much more raw data in bits per second can I transmit using 32 ApSK and a roll-off factor of 0.2? These all, by legacy, fit into 6 megahertz bandwidth channels. We'll come back and review the answer when the music's over. Okay, we're back. And let's see how, let's work through this, because it's a good exercise to work through. If I have binary phase shift keying, basically transmitting pulses plus and minus amplitudes, 1 bit per symbol, and I have a 6 megahertz symbol, and I'm using ideal sync functions for my pulses, no roll-off factor whatsoever. So remember, the Fourier transform of sync pulse is a perfect box. It takes ideal hardware to do something like that. It's not realistic, but let's say for sake of argument, then what is my bit rate in a 6 megahertz channel? Well, the distance from the peak of the sync pulse to the first periodic 0 determines your symbol period. And in the frequency domain, that sync function has a 1 over T sub s bandwidth. So if I have a 6 megahertz BPSK signal with 0 roll-off, that gives me 6 megabits per second. So now, armed with that information, if you didn't know it already, let's do the DVBS problem. We said that the original satellite digital video broadcasting standard was 6 megahertz of bandwidth, and it used QPSK, so there's 2 bits per symbol. But we have to adjust for the fact that instead of a sync pulse, we're using a roll-off factor of 0.35, which means I have 1 plus my roll-off factor of 0.35, determining the number of hertz per symbol. It should actually be hertz seconds per symbol, really, to get the units to work out here. 1 over symbols. So basically, if I had a roll-off factor of 0, I would divide this calculation by 1, because I have BPSK or QPSK with perfect symbols. But we know that when the roll-off factor is 0.35, I have to sacrifice, kind of broaden my time domain pulses in order to squeeze all the spectrum into my allotted bandwidth, because I got that roll-off to contend with now. And so if I do this calculation for DVBS, I get 6 times 10 to the 6 times 2 divided by 1.35, or 8.9 megabits per second. If I look at the parameters that I gave you for DVBS2, we said same 6 megahertz channel. If I'm using 32 ApSK, that's 5 bits per symbol. And what's more, because of the evolving hardware considerations that were later available, I can actually generate tighter roll-off pulses. That was a tighter roll-off up to 0.20 hertz seconds per symbol. And so what does that calculation wind up being? That comes out to a cool 25 megabits per second. So in terms of just the ability to push bits across the channel, this was a significant increase and improvement in the original satellite digital standard. In order to get that 25 megabits per second, though, however, you have to have a pretty clean channel, and you have to be able to sense that you have a clean channel in order to transmit. Anybody have any questions about that calculation? You could reproduce it on a test if you needed to. Now, that's raw bits going through the channel. That does not talk about the error correction coding. We said that there was Reed-Solomon encoding used in DVBS. Here, for DVBS2, something was written in the standard involving low density Parity Check codes, LDPC. And these were actually invented back in the 1960s by a PhD student, Robert Gallagher, I believe his name was. He did his PhD dissertation on these types of codes. And then people forgot about them because you couldn't build them. They were too complicated. It's interesting that so much of the 1960s and 70s were spent dreaming up interesting communication algorithms that they couldn't have possibly implemented in 1960s and 70s hardware. And you had to wait until the 90s when the digital hardware kind of caught up with these ideas. And a lot of these ideas were rediscovered or repackaged as, oh, we can finally implement them. And a lot of research opened up on these ideas again. But it's interesting in the world of coding theory, up until the 1990s, you pretty much had these same kind of codes available. There were these convolutional encoding techniques that people used. And then there was a whole family of block codes like Reed-Solomon, Bose, Choudhury, Hockwangimp. Nobody ever calls them that. They just call them BCH codes.
and a family of codes that did a pretty good job, but were always about like 7 or 8 or 9 dB away from the Shannon channel capacity limit. And there's this theorem that says, you know, to get the limit, or this philosophy, it says really you just need to make a more complicated code, right? The simpler your coding mechanism is, the harder it is to get the Shannon channel capacity theorem. We talk about this at length in the video. We show how increasing codes increases the coding gain of a system. So what you add is in the 90s, this kind of, people were even coming up with like this idea of a theoretical quasi-limit on data transmission. And he said, well, yeah, the Shannon channel capacity theorem says that you should be able to send so many bits per second, but practically with realistic hardware, this is what you should be able to send. And it'll always be like 5 or 6 dB away from that limit. So that was sort of the landscape in the 1990s, but then all of a sudden all these digital technologies were becoming commercially available. You could put them in cell phones and off-the-shelf satellite receivers. There were these 2 French guys, these mathematicians, a mathematician and an engineer, I think, Claude and Baroa were their 2 last names. And one of them went to the other and said, are there any unsolved problems in communications theory that I can apply my mathematical expertise to? And so, well, yeah, coding theory, trying to get Shannon channel capacity. Nobody's done that yet. We've gotten close, but we're still like 5 or 6 dB away consistently. I said, oh, okay. So they went to the drawing board and worked on this problem, and they came back and they published a great paper in 1996 on a method of coding called turbo coding, which was basically 2 different convolutional encoders that were kind of interleaved and scrambled together, which you could iteratively decode and pull out the original signal. And voila, wouldn't you know it, we were within about a dB of the Shannon channel capacity using turbo codes. Well, that was really really big and popular. I remember my digital communications teacher, I'm trying to think when I took that, it might have been around 1996 or 1997. He got back from a conference and he said everybody was all at Twitter about these turbo codes. Lots of sessions on how turbo codes operate, how to tweak them, how to design them, how to make them work optimally. And then shortly after that, we kind of rediscovered these low-density parity check codes, which are related in a way. And between the 2 types of coding sequences, turbo codes and LDPC codes, we've now come up with a beautiful tool set for almost always getting pretty close to the Shannon channel capacity limit for a digital communications channel. And so I'll give you a very brief overview about how these work. If you do a parity check, let's say I transmit 2 bits. I transmit 1 and a 0. What is the parity of that transmission? I already mentioned it earlier in the lecture. You exclusive OR all the bits together, and whatever's left over is the parity bit. If I had 2 zeros, I'd have a parity bit of 0. If I had 2 ones, I'd have a parity bit of 1. If I have a 1 and a 0, that's a parity bit of 1. So now, I can make something called a product code by taking a set of data. Let's say I've transmitted 1, 0, 1, 1. I first rearrange this into a square matrix where I put my 1, 0 on the top and my 1, 1 on the bottom. And now I do a parity check. 1, 0. This is odd parity. This is even parity on below. I do a parity check on the rows, and now let me also do a parity check on the columns. And in fact, I will do a parity check on my parity check bits. So 1, 1, that's 0 parity. 0, 1, that's 1 parity. And 1, 0, that's 1 parity. So now I started off with a 2 by 2 bit matrix, or 4 data bits. And now I've got a 3 by 3 coded bits. If I wanted to transmit, that would now require 9 coded bits of
transmitted data. So, now I could transmit this as a signal 1, 0, 1, 1, 1, 0, 0, 1, 1. And the interesting thing now is that I now have enough data here to figure out not only if I have received a bit in error, but I actually have enough information to correct the bit that I've transmitted in error. Right? Let's say that when I reconstitute my block, I transmit with an error. So let me go ahead and write this in. 1, 0, 1, 1, 0, 0, 1, 1, and let me put in a bogus transmission. This was supposed to be a 1. I'm going to transmit it as a 0. But of course, I don't know this at my receiver that I've received an incorrect bit, right? But I do know that the parity doesn't match. Look at this. This column is in error because the parity doesn't match. This column is okay, so I'm not even going to highlight it. Let me take my highlighting off. This column is okay here. This is the one in error. Now when I look down the rows, I see that this column is okay. This column is in error, and this column still checks out. Actually, I don't even need to do that one because I'm more worried about it this way. So look, I've triangulated. I said, I know that there's an error, and I figured out where the error is. It's the intersection of these two rows, this row and this column. So you can think of a product code like this as simply a giant game of binary Sudoku, right? You ever play that game where you try to figure out what are the missing numbers? It's the same thing. What are the numbers that are bits that are in error? So when I receive the signal, I know that I just need to flip whatever bit that is, and I can recover the original data stream. I'll use these bits to figure out the parity. I'll flip the bit, and there I've recovered my original data. Yes, Muliang.
So, Doctor, if there's a n by n matrix, and there are 4 spots like AIJ, AIK, some MJ, AMK, and that they are actually both flipped.
Yes.
Both has errors. On one side, the parity check will give the same results.
Yes, yes.
Yeah, how it will be identical.
So the scheme that I've shown here only works for correcting one error. If you have more than one error, this simple scheme doesn't work, right? Now, hopefully, first of all, notice the rate here. The rate here is actually fairly good for an encoder. For every 4 data bits that I transmit, I send 9 coded bits. And if I want to be able to correct more errors, I have to build more complexity into my coder. 2 types of complexity. First of all, more redundancy, so I can lower this, what's called the coding rate here. And then really to be an effective decoder and a forward error correction coder, I need something that's much more complicated as well. Something that folds in extra data bits. So practical LDPC codes are much more complicated than this, but they're built upon the same basic idea. I'm using parity checks, and I'm folding a bunch of these product codes into my computation in order to recover the original data. So when we go to when we go to the DVB S2 standard, there's actually a whole range of codes starting from 1/4 all the way to 9/10 that you can specify. Here, these low order rates are used for crummy QPSK links. That is, by crummy, I mean low signal to noise ratio. So it's interesting that the coding theory and changing the coding rate gives you an extra degree of freedom that the modulation scheme does not give you, that the signal constellation selection does not give you. You know, if I have a very high signal to noise ratio, then I use one of the coding rates up here for my 32 ApSK or my 16 ApSK, because by definition I have a pretty high signal to noise ratio. Those constellations have to have a high signal to noise ratio to be detected well. So we lightly encode them with not too much redundancy, because we're already going to be able to get a pretty good data rate out of them. Then if you go down, if your signal to noise ratio degrades, then you start ratcheting down to 8 PSK and then quadrature phase shift gain, which is just really 4 PSK, right? And then if you start getting worse, what do you do? If your channel gets noisier, what do you do after you hit QPSK? Well, there's no way to go down. I could go to BPSK, but that doesn't really help much. I get kind of that extra channel for free on QPSK. So I'm kind of limited. I can only send so many bits per second. So what you have to do then is just start to add more and more redundancy. Lower your coding rate, add more redundant coding bits, and this will allow you to overcome the noise up until you hit the channel capacity of the link, and you just can't send any more bits. It's too noisy to send digital data at a minimum specified bits per second. And so there's a whole bunch of selectable rates in between these two values, 1/4 and 9/10, that allows you to transmit and make the most out of your radio channel. Now, some things that are on the horizon here that aren't necessarily in the standard yet, but people have talked about improving or incorporating into DVBS2. First of all, one is not really a standard, but rather something people are looking into: iterative decoding at the receiver. So in a classic communication system, you detect your signal and you figure out what constellation point you received a symbol. And then once you're done detecting all of your signals, you run those bits that you've calculated through a decoder, right? Well, it turns out that you get the best performance if you kind of do those operations together. And it's kind of hard to do those operations together. So instead what you do is something called iterative decoding, where you estimate your symbols and then you run them through the decoder. And then you go back and look at the thing and say, well, are those the symbols that I actually transmitted? Can I correct some of my symbols? Because maybe I made one of the interesting things you can do with detection, and this is, you'll get into this if you take your digital communications course, is that detections aren't necessarily binary decisions, right? They are from our point of view when we draw decision boundaries and say, did I get this point or did I get this point? But not all decisions are created equal, right? Sometimes my decision was very close to the actual point, and so I would review that decision with higher reliability. Other times I might have been very close to the boundary, so maybe I was a little skeptical of that decision. It could easily be this, it could be a 49% chance of being this other decision constellation point, and it was I only have 51% reliability that I transmitted this signal. So not all decisions are created equal, and you can actually develop a decoding algorithm that takes that into account. And then if you apply your error detection and say, well, I definitely know I sent these bits in error, so I'm going to make a better estimate of that, then you can go back and kind of correct your decision making, right? You say, well, oh, this checks out. I did receive this symbol suboptimally,
and it turns out I did actually make an error, so I'm going to correct those. And then I redetect and then run that back through the decoder again. I say, oh, you know what? I discovered even more errors. And you go back and you do those back and forth. And so it turns out that is really how you get the most out of a radio channel. You can ratchet down and get extraordinarily high reliabilities if you iterate that cycle multiple times. And that is actually one of Professor Valenti's claim to fame. He's an expert iterative decoder person, which is why I gave this lecture in satellite communications. So iterative decoding, that's one thing that people are looking to incorporate into satellite receivers, especially now that there's enough signal processing firepower to make it happen. And another future topic of investigation is constellation shaping. And constellation shaping is where you do not transmit on that outer ring when you're operating at very high signal constellations like B2 ApSK. You don't use the outer ring as often as you use the inner ring, because the inner ring is transmitting at low power levels. So what you do is you pre-code your signal so that you spend more time in the inner ring. And on average, when you normalize for total average transmitted power, that technique achieves closer to the Shannon channel capacity limit, shaves you like, I don't know, 0.3 dB or something, than when you do not pre-code your constellation. That's called constellation shaping. That's a whole other topic that people are investigating. And it has some particular benefits for 32 ApSK in the digital modulation standard that we're talking about. So does anyone have any questions about that? If not, I will stop it there.